All right, so we are still in section 2.5. So obviously chapter 2, section 5. We're still talking about exact equations and our ways of solving them. And the goal is still to be able to find the special integrating factor. Right? So now let's run into some trouble. In fact, I could have scratched the last part A video, and I could have actually just went right to this method because, as I mentioned, this is the way I learned. This is the way I learned how to find special integrating factors. I never learned any of the other stuff, but this is, I'm not gonna lie to you, I'm pretty excited to demonstrate to you what I had to go through. Are you ready? Okay, so let's do this. So let's go ahead and establish. So we want to solve the following differential equation. You can verify if you'd like, but I'm just going to go ahead and tell you right now it is not exact. The partial of n with respect to y does not equal the partial of n with respect to x. You can verify that. Furthermore, if you went in and you started to use those little formulas that we were using in the previous video, if you were to go down this path, you would basically never be able to get a finished product that is only a function of x or only a function of y. It's just not cooperating. So what can we do? Well, here's the game plan. We're going to distribute x to the n times y to the m. All right, so let's take this equation. We are actually going to distribute x to the n, y to the m. This is quite beautiful. So just imagine that this x to the n, y to the m is going to be distributed to each one of these terms. Okay? Let's do it. Let's see what that looks like. I'm probably going to have to start writing, then copy and paste and make it smaller so I can fit it all in. But ready? Let's go ahead and get started. So if we distribute, at first we're going to have 12 x to the n, y to the m. Oh, let me take away that parenthesis. Plus, all right, so now let's go to the next round of distributing. Okay, so does it make sense that when you have x to the n times x, right? X to the n times x. That's just x to the n plus 1, right? Just like x squared times x cubed is x to the power of 2 plus 3. You add, if like bases, add exponents. So this is going to end up becoming 5x to the power of n plus 1. Now we have to do y. So y times y to the power of m is going to be y to the power of m plus 1. Okay, so dx. Let me go ahead and copy that, or cut that, and paste it, and make it a little bit smaller. Okay. So nice. So now we have distributed our x to the n, y to the m to the first term. Now let's go ahead and start our distributing here. So plus, well, let's go ahead and do this. So this is going to be plus 6. That again is going to be x to the n plus 1. And now this is going to be y to the m minus 1. Oh, my apologies. Y to the m minus 1. All right, so that is distributing to this term. Now let's distribute to our last term. So that's going to be plus 3. Well, there's no other y variables in that last term, so that's just going to be y to the m. And that's going to be x to the power of n plus 2. Okay, so let me go ahead and copy and paste, or cut and paste, so that it's a little bit smaller. All right, dy, and that is obviously anything times 0 is still 0. So that gets us to here. All right, so how is this going to work? Well, we are going to now take the partial with respect to x and the partial with respect to y. So, but we're doing it for a different reason. We're not checking to see if they're equal to each other. So we want to take the partial of m with respect to y. We want to take the partial of n with respect to x. I'm not gonna lie to you, I am just so excited to be able to show you this method. I can't contain myself. Ready? So let's start. So I'm gonna go ahead and label m. So obviously this is m and this is our n. Ready? So let's take the partial of m and we're going to take that with respect to y. Okay. So let me just make sure you see the stuff that's happening here, right? So you got 12x to the n, y to the m. If you take the derivative of that with respect to y, treating x as if it were a constant, well, come on, you know the deal. What is the derivative of y squared? Well, it's 2y to the power of 2 minus 1, right? You always subtract 1 from the exponent. So we're going to just take this m, move it out front, and we have to remember to subtract 1 from it. So what is that going to look like? So that should be 12 m x to the n y to the, well, it was m, and now we have to, since we took a derivative, we have to subtract 1. All right. Now what about this nightmare right here? Well, again, since you're taking the derivative with respect to y, let's just take a look at the y part, right? So if you have y to the power of m plus 1, and you take the derivative of that, well, you move the m plus 1 in front, and then it's just a power rule, so then you subtract 1 from the exponent, right? Same idea, just like when we would do 2y to the power of 2y to the power of 2 minus 1. So if you had y squared, it's the exact same idea. So let's see what that looks like. So that's just going to be plus, okay, ready? That's 5. We'll go ahead and write that as, remember the m plus 1 is coming out front. And that is, we're still left with x to the power of n plus 1 times y to the power of, well, if you have m plus 1 minus 1, then you just have m, right? So y to the power of m. Okay, so now let's, I'll show you where we're going with this in just a second. So now let's go ahead and let's go to n, and let's take the partial of that with respect to x. So now I've took my time on the previous partial, but I'm gonna go ahead and expedite this process here, sorry. So 6n plus 1, x to the n, y to the m minus 1, plus 3n plus 2, x to the n plus 1, y to the m. All right, so let's just verify that everything looks good. So I'm taking, let's start with this term here. So taking the partial with respect to x. So we're gonna have, that's where this n plus 1 has to come out. So that's where this n plus 1 is coming from. And of course, if you have n plus 1 and minus 1, you just are left with n. Everything else stays because we're treating y as if it were a constant. Let's go here. If you have x to the power of n plus 2, again, you can see how that n plus 2 has to come out front. And then, obviously, if you have n plus 2 minus 1, then you're just left with n plus 1, okay? So, where are we going to go from here? So, the whole point of this method is because we only care about the coefficients. So let me go ahead and box in the parts that we care about. Ready? Almost there. Almost there. So in essence, the reason why we choose to multiply by x to the n, y to the m, what we are stating is we're saying that the special integrating factor is going to look like this: x to the n, y to the m. Let's see if I can write that better. And the problem is we don't know what n, and nor do we know what m is, but we know that this is what the special integrating factor should look like. We just don't know what is n, and we just don't know what is m. Well, notice that after you distribute, take some derivatives, we are going to set up a system of linear equations where I'm going to set these guys equal to each other. I'm going to set the coefficients equal to each other, and I'm going to take that system of equations that bears out, and I'm going to solve that system. Okay, so I'll write you a quick note of what we're about to do. So we are going to set the coefficients equal to each other. All right, let's just make sure we set the dx's equal to dx's and the dy's equal to the dy's. And we'll go ahead and do that right now. So that's going to end up looking like 12m equals 6 times n plus 1. And then we're going to have 5m plus 1 is equal to 3n plus 2. Okay. So let's go ahead and clean this up. Let's distribute that 6, distribute the 5, distribute the 3. All right, so what is that going to be? 12m is equal to 6n plus 6. and then we have 5m plus 5 is equal to 3n plus 6. All right, so we've ran out of space, so let's grab this. And let's go ahead and go to our next page. All right. Well, again, what we want to do is we want to set up a system of linear equations. And so all we want to do is we're just going to, remember the deal. You would normally have your x. You would have your x's plus your y's equal to your constants. So let's just take the m's, move them and n's and move them to one side of the equation, and any constants will go to the other side of the equation. We end up with 12m minus 6n equal to 6. And then 5m minus 3n is equal to, well, if you have 6 and you take away 5, you have 1. There's your system of equations. Okay, so at this stage, I mean, this is easy. This is just solve your system of equations. I don't care how you solve it. You can use the substitution method, the elimination method. If you know anything about matrices, you can set up a matrix to solve that system. You can RREF, you can REF, you can use inverse of matrices to solve. I mean, what Gaussian, I don't care how you solve this system. Just figure out what m is equal to and figure out what n is equal to. All right? So in this case, m would be equal to 2, n would be equal to 3, and guess what? You're all done. So remember, we started off with u, the special integrating factor was x to the power of m, y to the power of n, right? No, my apologies, I got that backwards, don't I? All right, so x to the n, y to the m. So this is where we started. You did a lot of work to figure out that you can plug a 2 here, a 3 here, and there it is. You have your special integrating factor. So x to the power of 3, y to the power of 2. And there you have it. There's your special integrating factor. Now we're gonna conclude both this video and this section. Let me just make sure you understand that clearly you still have all your work ahead of you to solve this differential equation. Okay, this whole video was me just giving you a way of finding the special integrating factor. You would still have to now take that integrating factor. What was it? X to the power of 3, y to the power of 2, I believe. You would still have to distribute that integrating factor in order to make this exact. Listen to me, because I know you're starting to daydream. You still have to distribute this to your original equation in order to have an exact equation. But I'm telling you that this method that I showed you here will always work. Okay? You might end up getting like y to the power of 0 or something like that, but this method will always work. So if you would like to use these little formulas, that's perfectly fine. Or you can just approach all of these problems the way we did in this video, which is, again, the way I learned it. And as you've heard me say many, many times, if you've happen to have had me over the semesters is, I'm telling you, the majority of your applied mathematics will all come down to a system of equations. It almost always comes down to a system of equations. So if you're in linear algebra this semester, while you're taking differential equations, you're in a unique position to see some of the stuff you learned in linear algebra be put to use in differential equations. But we are going to conclude. If you have any questions, reach out to me.